house. Since it was so dependent on our previous part, I even put in brackets at the end of it. If you can't do it, use this number as the answer. And that way you're not floundering around. So if you get stuck in a section, you just go, oh, I can't do this right now, so I'll just use 10 as the answer and I'll move on. Psychologically, it didn't work out that way, where too many students couldn't do that problem and then they just stopped, as opposed to using the number I provided for them. But I would recommend that you slowly sort of work your way through that. Now, I also have provided answers to it, so that if you need part C to do part D, because part D is a conservation of energy, then just look at what the answer to C was and use that number. Now, the reason I bring this up now is we're about to do, I believe this was the very beginning of the Rube Goldberg test. Moments of inertia. They had a wheel here, another one connected here, and a rod sticking out. There was a string attached here, the mass hanging. And so the first part of the question is, it might not be exactly what I have there, but close enough. What is the moment of inertia of this rod if it's rotating about its center? So this is a rod sort of attached to a wheel here, and attached to this wheel is a smaller wheel rotating about the center right there, and then attached to that is, I have a mass attached to a string and wrapped around. So what happened is that this thing moved, this thing fell, this rod goes whipping around, smacks into something else, a collision. That goes moving on, then goes down the hill, conservation of energy, smacks into something else, and then hits a spring and oscillates back and forth. That oscillating back and forth was attached to another string, which then vibrated and made a noise on paper. Thus Rube Goldberg. If you're not familiar with it, with who Rube Goldberg is, you should look it up. Some really interesting designs. It's even a Rube Goldberg contest. So, thin rod. I'll make up numbers here because I can't remember what I had before. Let's make this 0.3 meters. The mass of the rod is 0.5 kilograms. The wheel here, radius is 0.6 meters, 0.2 meters. The mass of the big wheel is, we'll make that 1 kilogram. The mass of the little wheel will make 0.4 kilograms. I don't think I'm using 4 yet. Make this mass 0.7 kilograms. And that should take us through, well, a lot of what we're doing right now. We've covered all the bits of it. If I just said, work on it for the rest of the class, some of you will probably get stumped and based on previous class experiences. Some of you get psyched out really quickly. I'm hoping not. But apparently it happens. So, starting out, mass of the rod if it's rotated out of the center. Now, do assume that the rod is magically attached right here, that it's not embedded in it. So it's just like a rod somehow attached to a wheel, like that. I rod about the center of mass. How would you do it? Either you haven't caught up to the question yet, or you're way overthinking.
I'm still writing.
Okay. Give a little bit more time, and Brandon, when we get the nod from you, I'll ask the question again.
Okay.
that as a nod. So, I want the moment of inertia of that rod if it were rotating about its center of mass. How would you do it?
Let's start by writing the formula.
What is the formula?
I equals the sum of mi.
Ooh, you're going way back. There's a much simpler.
Oh, yeah.
May God have mercy on your soul if you're going back to there. Thin rod, rotating about its center.
Is it the 1/12 ml squared?
That's the one. That's why you could have jumped ahead to, straight to the formula. Now, on a test, this is one of the formulas on page 330 of the text. On a test, it would be on the first page. I'm not expecting you to have that memorized.
So this is the 1/12 ml squared is a already given formula?
Yes.
Okay.
Yeah.
That's why I didn't say that, cause I thought it
Okay.
was problem specific.
Oh, no, that, if this were a calculus-based course, if I were feeling sort of sadistic, I could ask students to derive that on test, but no. I tend not to ask people to derive that level of formula. Parallel axis theorem we're good with, but no, that one's a pre-given. All right, so 1/12 ml squared. So once you recognize there's a formula there, probably the biggest mistake I see is people thinking 1/12 and writing down 1/2. Please make sure it is a 12, or perhaps I'm just projecting on that one. That's one of the big mistakes I make. So it's just 1/12 times 0.5 kilograms times my length of 0.3 meters squared. And use a calculator, and somebody's gonna tell me the answer. Could be all zeros there.
I got 0.00375.
Oh,
Yeah,
okay.
you're good.
Units? Meters per kilogram, is that what you said? No, not quite, Ed's disease there.
Kilogram per meter.
Ooh, still Ed's disease. Have I talked about Ed's disease?
I don't think so.
Ed was a student I had in my first year here, sat back there. Always like, whenever he's doing several units, he would throw the word per in there. Per means division, we're not dividing any units here. And I talked about Ed's disease for a number of semesters, and didn't realize it at the time I was doing my Ed story. Actually had Ed's daughter in my class. So, Ed later went to Appalachian, became an engineer. Presumably he got over the per. All right, say it again?
Kilogram meters.
Squared.
Square.
There we go, kilogram meter squared. Yeah, there's no one word unit for this. Now, since this whole contraption is going to be rotating about the center here, what is the actual moment of inertia on the rod about the axis of rotation? Because it's not rotating about the center of mass, but it's rotating about this point. or how we define it.
What's the subscript on there for the second?
Oh, axis of rotation, I did O apostrophe or of, so axis of rotation.
Okay.
Because the actual axis of rotation is the center of the wheel.
Would it be the same formula, but the L would change? Yeah,
Not the way that I presented the formula earlier.
okay.
You can make an argument along that path, but I think that's a long route to take.
We wanted to,
So, because I'm not rotating about the center of mass, what am I gonna use?
The parallel axis theorem with the.
That's the one. So it's the rotation about the center of mass, 1/12 ml squared, plus the thing we need to take into account, the mh squared. So this is 0.00375 plus, because we've already done that part. My mass is still 0.5. What is h? Oh, shit, my answer first. How far did we move the axis?
.75 meters.
Yes. We move the axis from the center of mass to the rod. It's basically, it's the radius of the big wheel plus half the length. 0.75 squared.
I got .285.
Yeah, same thing.
For the whole thing or just that part?
The whole thing.
Units?
Kilogram meter squared.
I hope so. All right, so that's the moment of inertia of the rod rotating about the center of the wheel. And again, the rod is not driven all the way through here, the rod's sitting right there. Next, what is the moment of inertia of the big wheel? And then what's the moment of inertia of the little wheel? So, at this point, I need to give you a little bit more information. I am considering them discs as opposed to, a spoked wheel or something like that. So, what is the moment of inertia of a disc? Well, I come over to page 330, and they tell me the moment of inertia of a hoop about the cylinder axis. So that would be a hoop as if the spokes were, we could ignore the spokes, close enough to a hoop. Or there's a hula hoop over there, rotating about its center. Annular cylinder, about the cylinder axis. What's an annular cylinder? You would have dealt with it in the first lab.
just solid.
Or the other one. Not solid.
The hollow out cylinder.
Yeah, so you basically, it's a ring, because, so you got, otherwise they just call it a cylinder or solid cylinder. They give you the moment of inertia of a solid cylinder about the cylinder axis. Cylinder about the central diameter, and that second one was cylinder. There we go. So ignore the little nut right there. So the first one was a cylinder rotating about this axis, and the other one was a cylinder rotating about that axis. Thin rod about its center, thin rod about the end, solid sphere about its diameter, thin spherical shell about a diameter, in other words, like ping pong ball, hoop about any diameter. So the first, earlier it was a hoop rotating about the center, and this one, the last one, is a hoop rotating about that. And then a slab rotating about its center. Ignoring the feet, so slabs rotating about its center. So of those, which covers the disc? I didn't use the word disc anywhere in there. So we had hoop, cylinder, rod, sphere, slab. Which one of those would we use for a disc?
Cylinder?
Yes. What's the difference between a cylinder and a disc?
The, width, I guess you'd call it.
At what point does a disc become a cylinder?
When you decide so.
Yes, pretty much. Yeah, mathematically, there is no difference between a disc and a cylinder, especially if it's rotating about the central axis like that. Now, the textbook does, and I got this off on purpose because I want you to think about cylinders and discs being the same thing. It does say solid cylinder or disc. So we have a cylinder or a thin cylinder or disc rotating about its center. The formula is 1/2 mr squared. So 1/2 times 1 times 0.6 squared is for the big disc. This small disc is 1/2 times 0.4 times 0.2 squared. And so this is 0.18 kilogram meter squared for the first one. And the second one,
Yep.
sorry. My recollection was that this was part 1A, or A1, A2, A3. And then the last part for the moment of inertia, this first part is just about finding the moment of inertia. What's the total moment of inertia of this whole thing spinning about the center? Ignoring this. Because we don't have, this is not a standard shape. By having two discs stuck together with a rod sticking out of it, that's not in the book. How do we find the moment of inertia of that whole thing? Yes. Because remember, ultimately, moment of inertia, as Brandon was saying earlier, is just the sum of mr squared. It's just a big sum. How you break it up is up to you. So I'm going to break it up into a rod, big disc, and a small disc. And so my total moment of inertia is going to be 0.285 plus 0.18 plus 0.008. And doing the fancy math here, so we've got a 3, carry the 1, 7, carry the 1, 0.473
Yep.
kilogram meters squared. Any questions? All right, so now we have this mass falling. As this mass falls, this thing rotates. Assume that the center of mass still stays here, that the acceleration is constant. force diagram. I got this big monstrosity of that, and then I have a mass here, and then I have a rope. Assume that the rope is almost ideal. That there is friction between the rope and the pulley. However, the rope is not slipping. And you probably could have just the rope tied to it and still keep it ideal, but either way. The rope is not slipping as the mass falls, the rope goes with it. But we are now dealing with force diagram of this. Okay, we got tension on the rope, I got tension pulling down here, tension pulling up there, tension pulling up there, tension pulling down there. And that, the tension on the wheel is on the smaller wheel, because that's where the rope's attached. Right, so tension done.
There's no other.
All right.
Are we counting that giant monstrosity disc with the disc and the stick as one solid object, or do we need the normal force for all of them?
No, we treat it as one, the spinning thing is one object.
Oh.
You could break it down if you, again, masochist, but,
I'm good.
alright. What other forces are involved? Is it friction? Yeah. There is a way that I laid it out, but actually friction's gonna end up being an internal force here, so we actually don't have to worry about friction. So, I'm gonna go yes, but ignore.
We got gravity pulling down on the box.
Okay. So weight box, and I guess we threw the ground in there, weight box.
So there would also be weight on the, wheel.
Yes. Weight. Wheel.
You said the rope was almost ideal?
Yeah, that, more I'm thinking about it, just treat it as ideal for this. Okay. What's holding the wheel up? Is it rope? No, okay.
The rod is.
Yeah, there's some, we don't know what it is. This might be an example of other, or if you just imagine that there is a rod there. If there is a rod there, what would the force be?
Normal force.
Yeah, it would be a normal force.
Okay.
Or treat it as an example of other, we know something's holding the wheel up. And that's sufficient for what we need. Because what I primarily care about are this mass and the wheel. Because now we're about to do some equations of motion. Yes, right, because I heard some excitement over there. How many equations of motion are we gonna have?
Two.
Right, so, YJ's hand gesture first, Y2.
Up and down.
Is it, that's 2 right there, up and down is
Like 1 and 2.
the 1 and 2?
Yeah.
Oh, let's see what that does. All right, so let's go with that. It's actually gonna be 3, but let's look at it. If you just think, if you're thinking 2, we have Y minus, oh, let's make up positive. And like down positive there. So for the wheel, so we have Y minus Ft minus the weight of the wheel equals 0. And for the box, we have WB minus Ft equals 0. Oop, no, sorry. Equals mass of box times acceleration. Our unknowns, or our knowns more specifically. I can find the weight. I gave you the mass. We assume it takes place on Earth. That's easy enough to find. Mass, easy to find. Weight of wheel. I gave all the masses of the parts. That's easy enough to find. We have 3 unknowns. Because I don't know the tension. So this is the big clue right here that we need another equation. It's a good thing we're in chapter 9. Or 10, I can't remember which chapter this part actually is in. I blurred 9 and 10 together. We have something that is rotating. We're not worried, we do have this linear motion of the box as it falls, but the wheel is rotating. And so, yes, F equals ma is the basis of it all, but when we're dealing with rotation, we need the rotational analog of it. And what is the rotational analog of F equals ma?
Tau equals M alpha.
Not M. Alpha, yes. I, alpha. You did say M, right?
Yes.
Okay. Yes, the rotational analog of mass. Well, I, we know. We just did that. So recognize in which direction is the wheel spinning? Or what is the direction of, once it starts spinning, what is the direction of the angular velocity of the wheel?
Does it tell us which way it's spinning or?
Well, based upon the physics of it, if I have this wheel spinning right there and the mass right here, which way will it spin?
Negative K.
Oh, given, you would go to what I had before? It is coming out. You want that negative, who said negative K?
Me.
So you want K to be into the board?
Yeah.
Okay. Okay. So it would be in the negative K direction. Sure, why not?
Alright, let's go. Because Brandon said so.
All right, so the I part we know, that's the first part right there. This is one of those situations of, you know, if this is wrong, this was probably the easiest test I ever had to grade, because then I just type in what you actually got and all the rest of it just calculated itself. And so that was really nice that way. So if that was wrong, it was easy enough to offset of, okay, whatever you got for that, what should this answer be? However, we do have this, so I have a value for the moment of inertia. Because it is going to be accelerating in the negative direction, that'll be negative alpha. And now we're left with tau. What is the torque? Now before we do that, we need to do a little aside here about torque, of how do you actually calculate it. Yes, if I know the moment of inertia and the angular acceleration, I can find the total torque, but how do you find an individual torque? Besides Amazon. So, let's now do what physicists do. Take something that all of you have been doing for probably almost all of your lives and analyzing it, and basically to take all the flavor out of it completely. I want to shut this door over here. How do I shut the door? Push it? Is that what I heard?
Yeah.
All right, so I will push it.
I would've said pull it, so that means it's been on the other side of the wall.
I can pull it too, and it still didn't seem to close it. So pushing and pulling is not sufficient to be able to close the door.
From the backside of the door.
From the, facing the door, no.
It gets hard to do this. I've also done this with tying shoes, but that's less physics application and more how you give precise directions.
Yes.
And with tying shoes, the difficulty is getting the students, is it the 1 rabbit ear or the 2 rabbit ear method? But anyway, back to the door. Yeah, Brandon just sort of stopped.
You push the side closest to you?
The side closest to me, that's this side right here.
Then you can choose any side.
Push it hard.
And in theory, if I push it hard enough, I don't think it counts as shutting if I do it all together.
Push it in the direction of its
Of its opening.
gravitational velocity.
So push up,
Push
push,
with its,
Push the door
Rotation.
towards its door frame.
push towards the frame.
Push it towards the door frame.
That's actually opening it a little bit more.
Go to the southwest position of the, go to the southwest position of the door and push towards,
Push
push
towards it?
towards west.
Oh, you're giving actual physical directions there. Alright, so let's assume that I now understand what you're talking about. You want me to push on this side over here? Is that, do you agree with that, or am I just doing another trick because I'm about to taunt you with the words you use? Alright, so I'm gonna push on the